Next one's a little bit different. We are taking the limits as x goes towards infinity this time. So we're not just plugging in some value of 3 or 4 or 5 or 6 or 100. We are going out to infinity. So how do we do that? Well, if we were to just plug in infinity into the top and bottom, what we'd end up with is infinity over infinity pretty much. Because x squared, infinity squared is infinity, and we're just going to end up with infinity. Bottom, same thing, plug in infinity, infinity. So we can't do that though. It's not how we want to manage infinity. What we would do then is we're going to multiply the top and bottom by 1 over the largest x value in the numerator, and the largest exponent value. So x squared from, did I say numerator? I meant denominator. From the denominator, 1 over x squared. Now I know in this case it's the same. They're both x squareds. So you kind of get lucky, and that's probably why I said numerator, because I was looking at that x squared. But I meant denominator. You want to multiply it by the highest power of the denominator of x squared. And here's why. Here's what we want to have happen. Since we cannot have 0 in the denominator, we want this term to be like a constant, like 1, 2, or something, where it doesn't zero out. And what we're using, which idea we're using here, is if I have 1 over x, let's say, and I'm evaluating the limit as x goes towards infinity. If I were to plug in infinity, 1 over infinity, 1 over a really, really big number is 0. And if you don't understand that process of how do you get 0 when you do 1 over infinity, just go to your calculator and just type in 1 over 2, 0.5, 1 over 10, 0.1, 1 over 100, 0.01, and then just keep doing that, and you'll see that pattern developing where it's just going to keep on getting smaller and smaller and smaller, approaching 0. So 1 over infinity is 0. That's what we're trying to get done here. We're using this fact that 1 over infinity gets us 0 to hopefully help us with this. And then on the bottom, that's not going to happen though. We're going to get 1, or a constant, using the fact that we're multiplying by 1 over x squared, because we're going to cancel out these terms pretty much, and it's going to make a constant. So let's go through this. On the top, I'm going to get 2x squared over x squared minus 3x over x squared plus 5 over x squared. Then on bottom, x squared over x squared plus 4x over x squared minus 3 over x squared. So 2x squared over x squared, because it's just 2x squared over x squared. 1 times 2 is pretty much what you're doing. And then 1 times negative 3x, so negative 3x over x squared. 1 times 5 is 5 over x squared, and so on. So then what ends up happening is, boom, x squared over x squared, which becomes 2, minus 3x over x squared is just going to be 3 over x, 5 over x squared, and this is the limit as x goes towards infinity. And on the bottom, same thing, 1, x squared over x squared is just 1, plus 4x over x squared is 4 over x, minus 3 over x squared. Okay. Now let's evaluate the limit as x goes towards infinity. So you're going to want to plug in infinity everywhere you see an x. 2 minus 3 over infinity plus 5 over infinity squared over 1 plus 4 over infinity minus 3 over infinity squared. 2 is just going to be 2 minus 3 over a really, really big number. Same thing I was talking about over here. 3 over a really, really big number is going to be 0. Plus 5 over a really, really big number. Infinity squared. 0. On the bottom, we get 1. 4 over infinity. 0. Minus 3 over infinity. 0. And look what happens. I'm going to go over here. 2 minus 0 plus 0 is 2. 1 plus 0 minus 0 is 1. So we get 2 over 1, which is 2. So we're going to end up getting 2 there, and we have to use this idea here, multiplying by 1 over the largest exponent in the denominator. And that's going to help us out, clean some things up, and we're able to actually simplify this and actually evaluate the limit as x goes towards infinity. Pretty good stuff there. I like those infinity problems. It's a fun process.